All right, should I start? I think it's 1:30. Are we still waiting? Waiting for a couple more people?
People coming in. It's okay if you run a little bit over time. We usually do.
Oh yeah, well, yeah, I'll try not to go too much over time. Not a lot. Not 1 hour over time. I'll stay less than 1 hour over time.
I have a kind of short clock.
No, I'll try and stick to it in an hour. Depends if there are a ton of questions, might.
But it's not a big deal.
All right. All right. I won't go crazy trying to stay under time. Yeah, I don't know. Sometimes people have stuff they have to get to right afterwards. So.
Okay.
Now, yeah, I saw Misha in his office. And
so we got this up for me. All right.
All right.
So, okay, so we may as well start. It's a pleasure to introduce Leon Fitzpatrick from Boston University. Leon did his graduate degree a few years ago at Harvard, and since then he's been on a very successful career at various postdoctoral places, and currently he is a faculty at Boston University. Leon does Conformal Field Theory, as you will hear, but he also sometimes goes into the more phenol areas, and is in particular very highly cited paper on nuclear effects and dark matter detection of all topics. So please.
Great. Well, thank you for the introduction. Thank you for the invitation. So today I'm going to talk to you, as the title says, about what we can learn about how we can use what we know about conformal field theory to say something about quantum field theories in general. And specifically, I mean, how we can take what's thought of as the CFT data, and I'll say what that means to learn, sort of do non-perturbative numeric calculations of observables in quantum field theory, things like correlation functions and scattering amplitudes. So that's sort of where we're going. So the motivation is we're basically trying to understand what happens in QFT at strong coupling. I think for this crowd, I probably don't have to say too much about why we're interested in this problem, but so anyone who studies quantum field theory, you immediately face this problem, which is that it's just very hard to do very much at strong coupling compared to what we can do at weak coupling. And this sort of shows up no matter how you sort of come to quantum field theory, I think. But for me, I felt like it became very tangible emotionally back when I was thinking about beyond their standard model building, trying to think about what new types of beyond the standard model physics could be out there, where there really is just a huge divide between what we can do at weak coupling and strong coupling. So weak coupling, perturbation theory, we've kind of, as a community, turned that into sort of an industry, which we can use to very quickly make a quite wide range of different models. We can very quickly see what those models do, how they behave, and calculate things in very high precision without too much trouble. The situation at strong coupling is very different. By contrast, it's kind of the Wild West. We can do some things, but we're much more limited at strong coupling. Right? It's very hard to get a sense of what the full parameter space is of possible new physics models at strong coupling. Right? Okay, so QFT at strong coupling is an important problem. And so a lot of people have spent a lot of time thinking about it. And there are various different approaches to QFT strong coupling. I've listed some of the big ones here. I think it's fair to say that probably the most popular, well-known approach is lattice field theory. There's a thriving community of physicists who basically dedicate their whole careers to advancing this tool, lattice field theory. There are a couple others. So I listed some of them here. One, which I've listed, is what you might think of as improved perturbation theory. So the idea that if you know enough about perturbation theory, you might be able to do sort of clever resummations to learn about non-perturbative results. Perturbation theory is very smart in a sense. And then two more that I've listed here are tightly connected, as I'll discuss. Most of what I'm going to be talking about in this talk is the fourth one, Hamiltonian truncation. And I'll say what this is. And it's going to be related to conformal bootstrap, which is another non-perturbative method. And I'll talk about the connection between these two. All right, but before I get into that, I just wanted to say a couple words about why you might like to have another method besides lattice field theory, why you might like to have an alternative complementary approach in hand. And there are a couple reasons. There's some things which are very difficult or impossible to do with lattice. One is you might not be able to put your theory on a lattice, right? So not all theories can be put on a lattice. So probably the most important example is chiral gauge theories, right? Which includes in particular our world. The standard model is a chiral gauge theory. So this is a very important case of theories. And they're also very interesting in their own right. Another reason is lattice has physical effects, right? The real, when we're often interested in physics where there isn't really a lattice, and so putting a lattice actually changes the physics. So if you were doing sort of studying the system at some temperature above the inverse lattice scale, for instance, then you notice that the lattice actually breaks momentum conservation, and so you can lose momentum to the lattice itself through what are called Umklapp processes. And so this is bad for trying to study something like hydrodynamics, where momentum conservation is important. And so the physics of what happens on a lattice is very different from what happens in, say, a real fluid, where momentum really is conserved. And probably the third reason is that when we talk about lattice, usually we mean lattice Monte Carlo. That's how lattice computations are usually done, is on lattice Monte Carlo, and that's an intrinsically Euclidean method, right? It lives in Euclidean space, and it can be very challenging to try and extract Lorentzian observables from that. Okay, so these are sort of some reasons why you might like to have another approach. Okay, so that brings me to a discussion of how conformal field theory can help us develop another way to get at strong coupling physics. So let me talk a little bit about the connection between conformal field theory on the one hand and quantum field theories more generally. And what I want you to have in mind is this sort of picture that I've drawn here, where this is sort of the idea here is this: the way you're supposed to think about what quantum field theory is, what quantum field theory really means, is that you have, first of all, a space of conformal field theories. Right? So think about RG flows, think about couplings changing as a function of scale. And at the endpoints of those flows, you have fixed points. You have a fixed point in the ultraviolet and a fixed point in the infrared. And those fixed points are scale invariant. And in a Lorentz invariant theory, they become conformal. And so the endpoints of RG flows are conformal field theories. And first, you're supposed to understand the conformal field theories. Once you understand the conformal field theories, then you sort of get everything else. And the way that works is you start with the conformal field theory in the ultraviolet, and you turn on one of the relevant operators in the conformal field theory. And a relevant operator pushes you, sort of becomes, pushes you down an RG flow towards a new theory. It becomes more important in the IR. And he pushes you down some RG flow towards a new theory. And quantum field theories are points along these RG flows, right? So this is one way of thinking about what quantum field theory is. So I like this picture very much. I find this to be a very compelling, beautiful picture of what quantum field theory is. But if all it is a picture, if it's right here, it looks like it's maybe just a cartoon. If it's just sort of intuitive cartoon, then I think that's sort of unsatisfying in a sense. So really what we would like is not just to have this as a picture in our heads, but we would like to turn this into a sharp computational tool. We'd like to take this and use this to actually compute things in QFT. Yes, Alexei.
So what happened? Is this really a general picture? What if the world is secretly a lattice, then the short distance theory won't be a CFT.
Yeah, if the real world really is a lattice, okay, then that doesn't really fit into this picture. I'm talking about physics, which has which really is a continuum quantum field theory, right? So I'm interested specifically in studying continuum quantum field theories in infinite volume.
Good.
Right?
So you take some CFT, let it evolve, and then deform it in order to stop its evolution to another CFT.
Yeah.
That's what you are doing.
Well, yeah, I mean, deforming it and then just flows to whatever it flows to. Yeah, it flows to something in the infrared.
Okay.
But also, how do the mass scales appear? That's an external input, right?
Well, no, so that's built into the deformation itself. So if it's a relevant deformation, then that means it has some energy scale associated with it.
But that can't be anything to do with the CFT, though, right? Because it's a measurable parameter.
Right, but that's the point. So the point is that you have a CFT. Are there any?
You're going to deform it with some mass parameter?
Well, yeah. So I'll write an example in a second, and it'll be really clear. But imagine that you have your action is equal to the action for the CFT, and then you turn on a deformation like this, which is some relevant operator, and this operator has some scaling dimension less than d. So that means this coupling has energy dimensions. All right, so that's the scale. Right. So once you turn on the deformation, the theory is no longer scale invariant.
Yeah.
Right. You've put in a scale.
Yeah,
right.
You're putting in the scale.
You put it. Yeah. When you exactly. So right. That's the point.
The CFT, right?
No. But the point is that this is an operator. This is an operator in the CFT. So if you know everything about the CFT, this is one of the operators in that CFT. Right. So the CFT knows about the ways you can deform it. Yes, Maxime.
Say that you first put it as a small perturbation, but then you evolve to the scales where it's no longer.
Yes, and that's automatic if it's relevant, right? That's what relevant. That automatic if its dimension is less than d, then it's automatically a weak deformation in the UV and a large deformation in the infrared.
I guess my point is that the CFT can't generate G. You see, a field theory can generate a.
No, you generate it. You put it in by hand. You're the one generating it, right? You're God. You put it in.
So
Right.
let me try to give an example. You take n=4 super means, which is conformal, and then you put here and there some mass terms.
Exactly.
And then eventually it can become even PCD if you want.
Exactly. Thank you. Yes.
Not much is left from, well, unless these mass terms are very small, then okay, you can still use conformal field.
There's that's a beautiful example, and the types of things you can get in infrared are quite interesting. Good. So right. All right. So this is the picture. The picture is that we have an RG flow triggered by relevant deformations. So I'm going to use the Hamiltonian language in most of this talk. So our Hamiltonian in this picture that I just showed you is the Hamiltonian for the CFT. And then the point is the full Hamiltonian is not the CFT Hamiltonian. The full Hamiltonian is the CFT Hamiltonian plus this extra term that we've turned on by hand. Okay. All right. And then, so how are we going to solve the theory? How are we going to do non-perturbed computations? The way we do this, we're just going to solve the Hamiltonian. Okay. All right. Sounds easy. How hard can that be? Okay. Of course, it's very hard, but that's the idea. So just to say a little bit more, this is kind of how the philosophy of how you approach the solution to all of quantum field theory. First, so you break it down. It's a hard problem, so you break it down into steps. You break it down into 2 easy steps, right? Step 1, which is easy, solve the CFT, and step 2, also easy, solve the RG flow. Okay, you might be skeptical that these problems sound like they're not so easy. Step 1 sounds okay. You might be willing to suspend disbelief for a minute. Yes, we're trying to solve a theory, but it's conformal. Famously, conformal invariance is very constraining, and this is sort of what goes into the conformal bootstrap. It's why the conformal bootstrap works, because constraints of conformal invariance are so strong. So you might be willing to sort of, sit back and give me the benefit of the doubt that step 1 might be possible. But then you get to step 2, and now it's just a generic QFT. That sounds crazy. How could you possibly hope to solve the RG flow? It's just, there's no conformal invariance anymore. And what I'm going to tell you is that in some sense, step 2 is actually the easier step. Okay. If you really come along and you do step 1 for me, you solve the CFT, completely solve it, hand me all of the CFT data, and you just hand it to me, in some sense, step 2 is actually not so hard by comparison. Okay. All right. So how do we do that?
Excuse me, may I ask you? Okay,
Yes.
I understand. You solve CFT1.
Yes.
Right? Then you assume you solve the RG flow.
Yes.
You don't want to flow all the way to CFT2, right? You want to stop. You're interested in quantum field theory without conformality, right?
That's
or
right.
Not interested in CFT2.
So it depends. So it might be the case that the deformation gaps out the theory so that there are no massless degrees of freedom anymore. And then, you flow into the IR and the IR is just trivial. There's nothing left. Or it might be the case that you actually do have massless modes in the IR even after you turn on the deformation. And then in that case, the goal, you are actually interested in the new CFT in the IR, right? Yes, Fiona?
But so suppose that I just have a quantum field theory, which is not conformal.
Yeah.
How do you find the right CFTs to start it?
Yeah, well, you have to be a little bit clever, but I would say there's a large class of QFTs where we know how to find UV CFTs that flow to them, right? So if you have some example in mind, not in every case, but in a very large number of cases, we know how to embed them in a theory where they flow from some UV fixed point. So for Misha's point, imagine you started with QCD in the conformal window, and you turn on one mass term. So you take number of flavors to number of flavors minus 1. So if it's still in the conformal window, you flow from CFT UV to CFT IR. If you add enough mass terms, eventually the theory confines and it will be trivial in the IR. Those are both interesting cases, right? So it's up to you, right? It depends whether the theory in the IR is a CFT or whether it's trivial and gapped. Depends on the specific case you're looking at. Okay. Yes, Alexei.
I'm wondering what counts as having a solved CFT. So for example, if you have an N equals 4 superangles,
Yes.
4D,
Yes.
at smaller tooth coupling,
Yes.
is that solved by this definition?
Yeah, I would say that's solved if it's a small touch coupling because you can compute all of the scaling dimensions and OP coefficients if you're willing to work hard enough.
But then if step 2 is easy, then you solve the equals, right?
Yeah, that's right. But no one has actually done the work to do all that. But yes, that's the idea. That is the dream. So I want you to have that in dream in mind, right? That is. Thank you for. Yeah.
Small coupling. You solve for superior. It's
Yes, but what I
which
heard is not TCD.
There is no scale parameter.
I know, but
It doesn't flow anywhere.
But Misha, the philosophy of this talk is that having solved the CFT, you can now perturb it by relevant deformation, like your mass term.
Yes.
And if you do this to N equals 4 with a small tooth coupling and turn on a mass term, the thing you get in the IR will be Yang-Mills. So
Yeah, but you won't be able to.
So you're kind of let me just say something. Let me just interrupt for a second because I would like actually to say something, Misha, but I think it'll clarify the point if you just let me say something. I'm just going to talk because I do have something to say. So the point, think of this, Misha. Imagine that one example, one of the dreams that I'm going to come to at the very end, and I'm glad you mentioned this. I want you to have this dream in mind, right? So the dream is that you start with QCD in the conformal window with a large number of flavors. So it's very close to the edge of the conformal window. So the coupling, so it's a real CFT. So 3 colors, some large number of flavors. The coupling is small. It turns out I'm going to show you, it turns out it's about 1/20 in this case. So you really could just go out and compute all the CFT data. It's a lot of work, right? I'm not pretending that it's easy, but it's a program you could do. Then you go in. So to answer Misha's question, this is now, you're starting with a CFT. Now you go in and you add in 13 mass terms, 1 for 13 of the flavors, and you're left with 3 light quarks. All right. Now in the IR, the theory confines, and it's QCD. That's the idea. Okay. So, all right. So step 1 and step 2, obviously step 1 and step 2 are not easy. That's a joke that they're easy, right? But the point is possible, right? Okay. All right.
Can I ask a trivial question?
Yes, Sandra.
Yeah. On the level of solving RG flow,
Yes.
you really need to solve RG flow and you put mass term and you already know what happens.
I really mean you solve the whole theory. I just mean you just solve the theory. That's what I mean.
But
You just
know
solve
in advance what happens, or you can find some unexpected.
Well, the interesting case is where you don't know in advance what happens. So where, so sometimes to check the results, you want to look at cases where, special cases where you do know what happens in advance. But the point is that you also want to be able to compute things that you would have no other way to compute, right? So, good. All right. So, probably some of you don't know what Hamiltonian truncation is, so let me explain what it is. It's a very beautiful idea. It's a very simple idea, and I'm going to explain it just in a quantum mechanics example. It's actually extremely useful even just in quantum mechanics. So this is my favorite example of Hamiltonian truncation is the anharmonic oscillator. All right, so you can write the anharmonic oscillator as a piece we know how to solve, just the quadratic piece, which is the harmonic oscillator, and then an interaction term, the x to the 4. All right, and then the way Hamiltonian truncation works, the way we solve this theory is we're just going to diagonalize this Hamiltonian numerically. All right, we're going to put this Hamiltonian on our computer. We're going to type eigensystem and hit Shift Enter. All right, that's all there is to it. So of course, to put it on your computer, it has to be a matrix. We have to choose some basis. We can't just hand it sort of some formal abstract object. So we're going to choose a basis which is motivated by the part we know how to solve, right? The harmonic oscillator. We're going to choose a basis of eigenstates of the harmonic oscillator piece, right? So we all learned that those are states made by raising operators. So the nice thing about this is obviously the harmonic oscillator piece by construction is diagonal in this basis. And the interaction term is also very simple. X is just A plus A dagger. So you can very quickly compute these matrix elements. So you have some giant matrix, you throw it on your computer, and you just numerically diagonalize it. So unfortunately, this example, like all the examples that we'll talk about in this talk, the size of the matrix is infinite dimensional. And despite recent advances in computer hardware, we still can't fit infinite dimensional matrices on our hard drives. Maybe someday, but not yet. So we have to cut it down to size. How? And the simplest way to do that is just take a finite submatrix, right? Take some maximum oscillator number, n max by n max, and take that guy and put it on your computer. And then you want to take n max as big as you can, right? And this is what you get. So here I plotted the x-axis is n max, the y-axis is the energy eigenvalues, and you can see that as you increase the n max, they're converging. So this is eigenvalue 1, 2, 3, 4, 5. And this is, I forget what value of the coupling, but it's some order 1 value of the coupling, right? So I haven't used perturbation theory here anyway. So this is a very nice, very simple example. To emphasize how easy this is, I've put up sample code for how you would actually code this up, and it's really like basically 3 or 4 lines. This is the entire code that you need to do this, right? So these lines and then a couple more lines, basically that this is just saying take eigensystem and hit Shift Enter. And you get, if you copy these into your notebook and you Shift Enter, you will get a plot like this of the eigenvalues. It's just incredibly easy. If you've never done this before, I highly encourage you to try it. It's just extremely satisfying, all right, to get it so.
You lose accuracy once you move towards higher excited states.
You cannot
your
go
wave
to
function
the
will.
number of states, which is
The convergence, yeah. So the n max that you need, the higher the eigenvalue, the eigenstate is, the longer it takes, the larger n max needs to be before you start to see this convergence set in. That's right.
If somehow magically I would have a very simple solution for x to the 4,
Yes.
I would probably have an easier time of including x squared as a not a perturbation, but as a.
If you knew somehow how to write down the eigenstates, eigenfunctions exactly, then
For x to the 4.
yes.
Right.
But that's another way of saying yes, but you don't, right? So the nice thing about this is you really, this is something you really can do just very easily, right? You don't know the eigenstates exactly for x to the 4, and also, you may often we will actually be most interested in the lowest energy eigenstates, okay? But yes, you're absolutely correct that the convergence depends on which energy eigenvalue you're looking at.
Does it depend on lambda? Sorry, on the
G, yeah, the coupling, it also depends on G. So that's right. Well, and yeah, that's right. It also depends on G. So for larger G, you have to go to larger.
It's also, depends on what kind of questions you ask in the end. The energy, yes, but if you're asking questions about some matrix elements that sit at the far tails of the wave function, you will get probably not very nice results with truncating. So it's like depending on the question, your quality of your answer. wildly different.
Yeah, I guess you could find some question where it really depended on very precisely capturing. I mean, I'm not sure that there's anything as bad as you're suggesting. You know, if you wanted to look at the wave functions at very large values of x, the wave functions already in the harmonic oscillator basis are decaying exponentially. So if you're, if
your answer might be very small.
yes, exactly.
However, your answer might
Yes.
be infinitely larger than the correct answer.
Yes, yes. If you care about the ratio of the exact value of the
Yes,
wave
so
function at
it's-
very, very large x, yes,
Yeah.
yeah.
Or like, I might also have thought that if I was interested in something at like finite temperature.
Finite temperature is, I think this is something this is also very nice for because, okay, it's true that the convergence is slower the higher the energy eigenvalue, but it's still sufficiently fast and you can just crank up, you know, you can do on your laptop, you know, matrices without any trouble 50,000 by 50,000, right? So you have a huge, I mean, I would say this is actually a strength of this type of approach is that you get just a gigantic number of energy eigenvalues to pretty good accuracy, and you can just construct canonical and microcanonical ensembles, right? So I really don't see that as a weakness. I see this as one of the strengths. This is one of the few methods which just gives you access to just a huge number of eigenvalues, which is something which you don't get by most other methods.
Just a very
Yeah.
nice question. This concept of convergence here, is it the mathematical proven concept here up to a certain order, or it's really just you see as I increase the number of steps, the value of that?
In this particular example, this is kind of a special case, and I think you can actually prove, but the convergence in the anharmonic oscillator is better than most of the examples we're going to look at. Most examples we're going to look at, we're just going to numerically see how it changes as we increase the truncation. I will not do any, yeah. I mean, in some cases, I'll give you intuition for why the answer should be what it is, but I'm not going to have any rigorous proofs.
Okay, let's go to field theory.
All right, field theory. All right, good. So how do we do field theory? It's the exact same thing. We've set our Hamiltonian for a QFT is a CFT plus a relevant deformation. So let's do a simple example. The simplest CFT I know is a free massless scalar field. It's a perfectly respectable CFT. If you're in less than 4 dimensions, here are 2 nice relevant deformations you can add. Phi squared is always relevant. Phi to the 4 is relevant in D less than 4. So you can turn both of these on. And then again, we're going to try and choose a basis. We have to choose a finite set of states, of basis states to diagonalize the Hamiltonian. We're going to try and choose one which takes as much advantage of the conformal structure of the UV as possible. And so what we're going to do is we're going to choose states created by CFT operators in the CFT with dimension less than some truncation delta max.
But in field theory, you need mostly not the mass of the particle, but the correlation function. How are you going to?
I'll get there. Don't worry. I'll show you how to compute correlation functions. All right, good. So I'll say more in detail about what these basis states are, but for now, I just want to point out one advantage of this approach is that the Hamiltonian matrix elements in this basis are directly given to you by what we call the CFT data. All right, so the Hamiltonian, remember, it's the CFT plus a relevant operator, and the matrix elements of the CFT part basically are given by the CFT 2-point functions. And the matrix elements of the deformation of the interaction, notice since our basis states are created by primary operators, it's basically a 3-point function, right? So our bra is an operator, a ket is an operator, or interaction is an operator. This is a 3-point function. And 3-point functions in CFTs.
One question.
Yes.
You start expanding or your procedure around free field theory.
No expansion.
No expansion, your calculation, but you start from the from H, which doesn't have a mass term, right?
That's correct, yes.
So you are bound to get some severe problems in the infrared.
No. So you're thinking that I'm doing perturbation theory in this coupling, but I'm not doing perturbation theory in this coupling.
No, but this or relevant, you will. Okay. You said that your 2 CFT 2-point functions.
Yes.
You use CFT 2-point functions. For
Yes.
instance, the 2-point function in massless 5 theory
Yes.
is 1 over x squared. Now you start with this two-point function, you start calculating the various operators with the participation of Theorem.
Yes.
But you calculate it using the massless two-point functions, and this will sure lead to infrared problems.
I think you're imagining I'm doing some type of Feynman diagram expansion. The two-point functions are not ever going to show up. I'm not going to be computing diagrams where I have two-point
Okay,
functions.
can you show something less abstract than this general theory?
Yeah. Yes. I will show you. I'll be super duper concrete. I'm just trying to give you a sense of the construction, what goes into it. But I promise you I will get there, given enough time. All right. So let me tell you a little bit more about the basis states. So if you've spent a lot of time thinking about CFTs, you might think the most natural thing to do is radial quantization, where you map the system to a sphere. But that's not what we're doing. That would be a finite volume description. We want an infinite volume one. Here, what I really mean is we just take primary operators and we Fourier transform them and we hit the vacuum. That's how we're creating states. All right. So let me give you a super duper simple example. A free scalar field. If I take just phi and I Fourier transform it, then I get a creation annihilation operator, and I hit the vacuum with that. That's just a one particle state. Okay. More generally, you don't take O is equal to phi. You take O is equal to some product of phi's and its derivatives, and then what you get, if you think about that in the Fock space basis, this is multi-particle states with some wave function over the momenta. And the fact that the operators are primary operators corresponds to the fact that these wave functions are polynomials of momenta, but satisfy some primary operator condition, which exactly what that looks like is not that important. Okay, so that's how you should, in a free scalar CFT, this is what these basis states look like. Okay.
Can I ask an ignorant
Yes,
question?
yes, please.
Does this give you an orthogonal basis?
Yes, yeah, it does. Yeah, and that has to do with the fact that it's a statement in CFT that you can always, so operators with different dimensions are automatically orthogonal to each other, and then you can, the ones that have the same dimension, you can just diagonalize their two-point functions.
What do you mean by a particle state here? CFT, there is no just like correlation.
Yeah, so in general, there would not be any particles. This is the intuition in this case where it's a free massless scalar, and a free massless scalar just has massless particles. All right. So okay, here's another important technical point, which is everything I'm going to be doing is going to be in light cone quantization. So when I say the Hamiltonian, I mean the Hamiltonian that generates translations in the null direction x plus. Okay, so our Hamiltonian is p plus. P plus is the generator of translations in that direction. Our spatial direction is the other null direction as well as some perpendicular directions. Okay, and this is actually a rather gigantic simplification. Makes things much, much easier. And the reason is basically that it gets rid of this type of diagram where you have particles being produced from nothing. The most important of these is you get sort of vacuum bubbles. So in a generic truncation formalism in QFT, you have mixing between the vacuum and multi-particle states. But in light cone, you can't do that. That just has to do with the fact that the light cone direction p minus can never be negative, right? So the vacuum sort of lives in its own selection sector. So this allows us to take the infinite volume limit from the very beginning. All right, so this turns out.
Excuse me, isn't this the paradigm which had been explored by Ken Wilson and his collaborators for many years?
The one called DLCQ.
Light cone, yes, DLCQ.
Yes, discrete light cone quantization.
Take the QCD Hamiltonian on
Yes.
God, and then on the light cone, and then tricate it.
Yes.
Then do numeric calculation.
Yes.
And nothing good came out of this.
Yes, so this is a better basis. It's a different basis and it works much better. Okay, so what you're referring to is called discrete light cone quantization. It's not what we're doing. Discrete light cone quantization, you take the null spatial direction and you compactify it. And then you just look at the set of Fock space modes on that with momenta quantized because of this compactification. And you try and take your allowed momenta to be as large as possible. So that's the truncation in that setup. we're doing something different, which is infinite volume. We're using states created by Fourier transforms of primary operators, right? So these are wave functions, are polynomials in momentum space, right? So we're gonna be doing this one, okay? All right. Good. So let me give you, all right, so let me do the first example. I planned to do 2 examples, and I will try very hard to get through both of them. So the first example is phi-4 in 2 dimensions. All right, so just a potential via phi, that's a mass term and a phi-4 term. All right, there's a single dimensionless combination of lambda and m. We'll call it lambda bar. Let me just remind you what happens in this theory. So at very small coupling, it's just a weakly coupled phi particle, and the mass is very close to the bare mass. As you start to, and there's a Z2 symmetry in this theory, which is unbroken. As you start to crank up the coupling, the gap, the true physical mass starts to decrease. This is the leading term, which you can just compute in perturbation theory. And as you crank up the coupling, the physical mass gets lower and lower and lower, and eventually the mass squared gets driven negative. And then you can think of the potential of sort of developing a minimum away from the origin, and then phi rolls off to another phase where the Z2 symmetry is spontaneously broken. And the most interesting point, I think, the most interesting point is this critical point. Yes, it's the most interesting point. Is the critical point, which is it turns out to be the easy model. Okay, the 2D easy model, which is just a free fermion. Okay, it's not obvious that it is, but that's what it is. All right, so much formalism. Let me give you a real concrete example. Okay, so this is what the Hamiltonian looks like. To make it sort of something I could write on the slide, I chose a very severe truncation with only 2 states. These 2 are 2 states. So the Hamiltonian is just a 2x2 matrix. We can look at m squared, the Lorentz invariant m squared, which is p minus times p plus. And here is what that Hamiltonian is in this basis. All right, so one thing that's nice about light cone is m squared is linear in the Hamiltonian instead of quadratic. And you can just do a short calculation and you get these guys. And you can easily diagonalize this 2x2 matrix. You can plot the lightest eigenvalue and you get its blue curve. Okay. All right, so the point is not that this is a great approximation. It's actually not a very good approximation. But there are 2 points. The first is that this is a variational method. As you increase your basis, you have more variational parameters. So as you add more basis states, this blue curve can only go down and to the left. So you immediately know that the critical coupling has to be somewhere between 0 and where the blue line crosses the origin. And the second point is that by adding more basis states, you can systematically improve it. So here's what you get at delta max of 10. You get the new blue curve, delta max of 20, delta max of 30, and then finally delta max of 40. Okay, so already by delta max of 30, it's converged pretty well, and delta max of 40, it's super duper converged. Right, so you see the gap all the way to the critical point. And then in light cone, you can't really go past the critical point for subtle reasons that I won't go into.
Yeah, I probably asked before.
Yes.
And you can get exponent, right, for the mass. How the mass opens up if you go to smaller x.
So the way you would do that.
Just looking at the curve. And
you would think so. It's actually, from this curve, it turns out that you can't. You have to look at things like 2-point functions, which I can explain afterwards. All right. But yeah, that's one of the subtleties. But okay, I think it's not super important for right now. So here I want to answer kind of Mistra's point, which is, isn't this something that Ken Wilson and Stan Brodsky and Pinsky and Pauly all did a million years ago? And didn't, nothing good came out of it. Well, so first of all, I don't think it's quite true that nothing good came out of it. But also, one thing that you can see very directly here is that the convergence rate is significantly better with this basis. So here, K is the truncation parameter in DLCQ and the truncation parameter LCT. So for LCT, for light cone conformal truncation, that's the method I'm using. K is just the maximum dimension of operators. For DLCQ, it's the maximum momentum in units of the compactification. It really is fair to compare to K, because the number of states in both cases is just the number of integer partitions of k, right? So if k is the same, then the number of states is the same, and the size of the Hamiltonian is the same. And in DLCQ, that's this red curve. There was a paper just from a month ago where they put all this on a supercluster, and they did, I don't know, like 1 million states. And this is what they get. So here, the y-axis is the critical coupling. It's where that blue line crosses 0. And the x-axis is the truncation parameter. And in DLCQ, it converges like 1/square root of k, and in LCT, it converges like 1/k. Square root of k versus k is a big deal because the number of states grows very fast with k. It's the number of integer partitions of k. That's roughly given by the Cardy-Ramanujan formula. Also, you can think of this as Cardy growth from the Cardy entropy. So if you wanted to get critical coupling of, say, this value, and in LCT, you would need 20, delta max of 20, which is about 627 states. And for DLCQ, you would need 20 squared, which is about 10 to the 18 states. Yes, Fiona.
Sorry, is your y-axis, is that lambda, lambda minus lambda c, or this is just, like, where is the critical coupling?
This is where is the critical coupling. So this is if you, what I mean literally is if you, so there's some, if you choose some truncation, it's the value of lambda where this crosses 0. That's what lambda c is.
But the true value sits.
The true value is what where it would cross 0 at infinite truncation. Okay.
Which is close to 2.
Which is, yeah, it's 1.8.
Yeah.
That's what you get when you take k goes to infinity. So it's 1. That's right. Okay. All right. Good. All right, so we don't just care about the critical coupling. A lot of work has gone into computing the critical coupling, but in some ways it's the least interesting thing you can compute. What's more interesting is we care about correlation functions and scattering amplitudes and form factors. This is what we really care about. Okay, I don't know about you, but you probably are not super duper interested in the specific value of the critical coupling, especially because it's scheme dependent. So all right, so let me just mention some of the things you can compute. One of them is spectral densities. This is the Chilean-Layman spectral decomposition formula, which we teach in our QFT classes. And what's nice is you really can just use this formula, right? So this formula, you need to know the eigenvectors of the Hamiltonian, you need to know the eigenvalues, and you need to know the overlaps of local operators with those eigenvectors. You have all those things. You've diagonalized the Hamiltonian. You just have the eigenvectors and eigenvalues. You can just plug them into this formula, and you can sum over J, and you get the spectral density. Okay. So I'll talk about that sort of, but first I'm going to talk about form factors. Form factors are similar. You have the overlap of a local operator between two one-particle states. So one particle state is just an eigenstate of the Hamiltonian. So you have this eigenstate, and you can just sandwich a local operator between these two guys. That's a form factor. All right, so let's talk about this one first. So here's what I just said. Form factors are the overlap between a local operator, the matrix element of a local operator between two one-particle states. So recall that we're using this basis where our basis states are these Fourier transforms of local operators. So that means this matrix element, P1 operator P2, well, I can expand P1 in terms of our basis. And what I have is a Fourier transform of the Bra operator and the Ket operator. And so I'm just doing Fourier transforms of a CFT 3-point function. The position dependence of a CFT 3-point function is totally fixed by conformal invariance. So you can just do those Fourier transforms in closed form, and then you just sum up over these coefficients that you got from diagonalizing the Hamiltonian. So again, let me just give you a concrete example. Here I'm going to choose delta max of 5. And so now I have 4 states. Here's what the Hamiltonian looks like in this case. So before it was just the 2x2 upper left-hand corner. Now I'm taking a bigger truncation, so now it's 4x4. You can just diagonalize this. You look at the lightest eigenvalue, and here I've chosen arbitrarily. I've chosen some value of the coupling, and you get something like this. Okay, so it's just a sum over these 4 operators. And then if you want to compute a form factor, you just plug that in here, and now you get a sum over these Fourier transforms. And so you get something like this. You get a pretty good approximation to the form factor as a polynomial momentum. Okay. So how does that do? How does that compare to things we know. So, well, the easiest place to compare this is at weak coupling. At weak coupling, you can compute the form factors just using Feynman diagrams. So here I've plotted all these different lines. This is the form factor as a function of q squared, which is negative. The y-axis is the form factor itself. And blue line here is one small value of the coupling, orange is another small value of the coupling, and the coupling gets bigger and bigger and bigger, and it goes all the way, almost all the way up to the critical point. The critical point is 23 over 4 pi. I apologize for the different normalization, but I wrote things divided by 4 pi because different conventions were used in two different papers. But you see the blue line is from truncation, and the red line here is the two-loop result from Feynman diagrams. If we crank up the coupling a little bit more, it's still a pretty good approximation to the Feynman diagram result, but not quite as good because the coupling is larger, and so perturbation theory is not as good. And as you crank it up more and more, you eventually are just exiting the regime of perturbation theory, but you're still able to compute the form factor. What about scattering amplitudes? So in 2D, there's a cute thing you can do called Watson's theorem, which says that the elastic scattering S matrix is given by the form factor between the vacuum and 2 particle states divided by its complex conjugate. All right, so the elastic scattering S matrix is just a phase, and notice the right-hand side is a number divided by its complex conjugate, so it's also a phase. So you can get the elastic S matrix if you know these form factors, but we already know these form factors because we computed this form factor, and using analyticity, we can analytically continue in one of these energies, and from that we can get the matrix element between the vacuum and a 2 particle state. Right? So
it's difficult to analytically continue from an ensemble of numbers.
No, I'm not continuing for an ensemble of numbers. I'm continuing. So this is the fact that the light cone truncation preserves boosts along the null plane means for every different momenta, you just have to diagonalize in one frame, and you can get the others by boosting. So the momenta show up by doing the Fourier transforms of these 3-point functions. So you actually get an analytic function of momenta. So we're analytically continuing something which is not just a bunch of numbers, but is actually an analytic function. There's still some work you have to do because this, you don't know this exactly. You have to take into account truncation effects. So it's not totally trivial to do this, but you can do it, right? That's the idea. You know this as a not just at a bunch of points, but as an actual function. It makes your life a lot easier. All right, so what do you get for the S matrix? So here I've shown you the S matrix. It's real, the imaginary part of the T matrix and the real part of the T matrix. There's a lot going on in this plot, so let me just walk you through it. At weak coupling, we already know that the theory is supposed to be a weakly coupled scalar field. Very close to the critical point, it's supposed to be the Ising model, which is a free fermion. If you're not exactly at the critical point, but you're slightly away from it, two things happen. First, you turn on a mass term, and then after that, you turn on interactions, which is the leading irrelevant deformation. Okay, in this case, the leading irrelevant deformation is a 4 fermion operator. In CFT language, it's a TT bar deformation. So if you're very close to the critical point, you can compute the S matrix also analytically by doing scattering of weakly coupled fermions where they're scattering through a 4 fermion interaction. So let's focus on the imaginary part of the T matrix first. So here I've shown you a bunch of different lines. The bottom one is the smallest coupling. So blue is what you get from truncation, as red is the perturbative lambda phi to the 4 result. Right? So those are bang on. And as you increase the coupling and go closer and closer to the critical point, you're getting closer and closer to this black dash curve. That is the S matrix for a free fermion. So you see, we're actually we're seeing that the S matrix, as we crank up the coupling, it interpolates between a weakly coupled boson all the way to a weakly coupled fermion. Right? So we actually see the emergence of a weakly coupled fermion. We see the emergence of the 2D Ising model S matrix in the infrared. And then in the real part of the S matrix, so this part only saw the free fermion. The real part of the S matrix actually sees the 4 fermion interaction. So again, that's the black dashed line. And you can see the blue curve is where we get very close to the critical point, and it's very, very close to the black dashed line. And it's not exactly on it because we're not able to go all the way exactly to the critical point, just close. Okay. So okay, I'm excited about this. I think this is what I like about this is you really can see the transition as you crank up the coupling from a boson to not just a fermion, but actually specifically the Easing model fermion with the interactions that are allowed in that description. Okay. How many did I have for this? I think about 40,000 states, 40,000 operators.
Just curious, in terms of deviation from critical point,
Yes.
I guess it's variable x, right? I can see from here. Now on the top graph.
Yes. Yeah.
Okay, so in terms of deviation from the 1.8 and your
Yeah.
critical point, when you see free fermion behavior, how close you have to be to see this?
Yeah. So let's see. So the critical point is 23 over 4 pi, and this blue line is 18 over 3 pi over 4 pi. So what is that about?
Is it percentage or it's some sizable distance?
Yeah, I would say it's about 20%.
Oh, so it's sizable distance.
Yeah, I mean we're about right here, I think.
Mhm.
Right, so right around here.
Good to know.
Yeah. Which is why this blue line is not completely following this black curve. Because the closer you get to the critical point, the more you're removing this irrelevant. Sorry, the more you're just capturing the contribution from this irrelevant operator and suppressing all the higher order ones. Yeah. Yeah, about 20%. All right, so that wraps up my first example. So this is, now I wanted to move on to another example, 2D QCD and the chiral limit. It's a limit where the quark mass is very small, but not exactly zero. And we'll see how much of this I get through. But okay, so this is a very interesting limit. So why is this an interesting limit of 2D QCD? So I mean QCD with 3 flavors and 1 fundamental fermion. All right, so this is an interesting limit because in the limit that the quark mass vanishes, you have to have a massless pion in the infrared. Okay, so I've called it a pseudo Goldstone boson in quotes. Of course, there are no Goldstone bosons in 2D. Sorry, I'm using high energy language in this whole talk. 2D means 1 plus 1D, in case that wasn't clear. Right, it's not really a Goldstone boson. Really, it's there because of anomaly matching. So there's an axial anomaly in the UV, which has to be matched by a massless mode in the infrared. And you can see that very directly. So in the UV, since it's 2D, the anomaly is computed by a 2-point function, so just a quark loop. And the coefficient is just proportional number of colors. The pion, you can think of it as like ELI pi over F pi is QQ bar. So the axial current shifts the pion. And so the decay constant has to enter here this way. And so we can just compute the 2-point function in the IR. And we can match the anomaly coefficients, and we can actually calculate the pion decay constant this way. And just F pi is equal to NC over 4 pi.
Excuse me, do you see in your method that there is a order parameter psi bar psi, which develops an expectation value?
Yeah, that is a very good question. And I don't know the answer.
I think on the light bulb, no.
I think the answer is no. I think you don't actually. And I think it's because it's in 2D and there's actually no spontaneous symmetry breaking in 2D. So I think it's a little bit subtle what's actually happening with the VEV of QQ bar in this case.
Yeah, light cone is a very singular reference frame for work, and it doesn't reproduce all details. You can do, many people did it from the standpoint that you go off the light cone a little bit. And then it's a more regular point, and then you do the calculations, you see the fermion parameter, but then when the order parameter non-vanishing, and then you go to the light cone, and it's become a singular point, and you don't see it any longer. But that's okay. That's a side remark.
All right. So we are, let's see. So next, I wanted to say that you can say actually much more than just that, the decay constant. If we turn on a small quark mass, We actually know what the leading chiral Lagrangian is just by spurion analysis. So the quark mass explicitly breaks the actual symmetry, but you know that they have the quark mass and e to the I pi over f have to come together in this combination. So you immediately see at small quark mass, the action is just well described by this. So it is exactly the sine-Gordon model in the infrared. And you know, furthermore, you know the f of the decay constant. This is an old result. This was first derived, as far as I know, by Paul Steinhardt in 1980 using a very different method. So here we see how to get it by sort of more modern methods. And the nice thing about this is the sine-Gordon model is exactly solvable in 1 + 1D. So in the limit of very small quark mass, we can just check our results. All right, so people knew about the small quark mass limit. I just told you it was derived by the sine-Gordon description was shown almost 4 decades ago. But it's been very hard to approach this using Hamiltonian truncation methods. And the reason this has been challenging is that in the limit where the quark mass is very small, the wave functions for the eigenstates do something very funny. Right, so they actually near the boundary, when any of the moments of any individual parton becomes small, the wave functions go like some non-analytic behavior. They go like p to some power, that power is very small. Right, so that power goes like it's proportional to the quark mass. All right, so you're trying to reproduce this type of behavior, and that's just hard to do with a generic basis. It requires a very large number of basis states, so it leads to very slow convergence. Right, and you can check this in the formalism I've been describing in LCT, and you can also check it in DLCQ. The convergence is like 1 over the truncation parameter to the alpha, and remember, alpha is very small, so this is terrible. This is a disaster. Right, so you just can't do it. All right, so there's an easy way to get around this, which is we're going to use a different basis, one which sort of from the beginning captures this funny behavior. All right, and so what we're going to do, instead of making our primary operators out of the local fermion field, the local quark fields, we're going to make them out of a non-local operator, which you can think of as d alpha acting on the fermion. Right, now that's might sound like a dangerous thing to do, but it turns out it's easy to see that d alpha psi, because the UV theory is free, this behaves exactly like a primary operator with dimension alpha plus a half. So it's still, all its correlation functions still satisfy all the axioms of CFT correlation functions. It still transforms like a CFT primary operator. So you can still do all the same tricks that I've been describing.
Why isn't that local? You're just taking a derivative.
Yeah, but alpha is like 0.00001.
Oh, it's a power of a derivative, not integer.
It's not, yeah, this is not a Lorentz index. This is a power.
Oh.
Okay. So alpha is a tiny number. Thank you for asking. Okay. All right. So, but you can think of it in momentum space as like p to the alpha. That's what it's trying to do. Okay. All right. And you get much faster convergence. So here's what you get as a function of 1 over delta max. And here's the gap. First of all, it's converging like 1 over delta max now. And second of all, you actually, the coefficient of 1 over delta max is pretty small. You get a pretty good answer even at very small truncations. So let's check, is this the right answer? Well, like I said, we know what the right answer is because it's the sine-Gordon model. So one thing you know from the sine-Gordon model is that it's a bound state of 2 pions. You can compute their binding energy exactly. And for 3 colors, it's about 10% of the pion mass. All right, so here I've shown in red, blue, and green what we get from truncation. And then I've also shown on top of that what you expect from the sine-Gordon model. So the red curve is the pion mass that converges almost immediately. So this just looks like a constant. The black dashed line is the 2 pion threshold. And then the brown line I put in is the prediction from the sine-Gordon model. That's the slight shift downwards by this binding energy. And you see the blue curve is what you get in truncation. It's already converged pretty well by about delta max of 6. By delta max of 12, it's sort of indistinguishable. Okay. But we can also compute correlation functions. All right. So I mentioned we can compute spectral densities. And part of the point of the Chiral Limit spectral decomposition is that time-ordered correlators are just integrals over spectral densities. And if you plug in this formula, that's just a sum over things like this. So a sum over these overlaps between the operator and the eigenstates divided by p squared minus eigenvalue squared. All right, so you can just plug into this formula and you can compute the time-ordered 2-point function. So why do you care? Well, one useful thing about spectral densities is the stress tensor spectral density is particularly interesting. It's actually directly related to Zamolodchikov's C function. So his famous C theorem that says that there's a C function which counts the number of degrees of freedom roughly, and it's monotonically increasing, right? And here, actually, in this description, it's just obvious that it's monotonically decreasing as you go into the infrared. It's an integral from 0 to the energy scale of a manifestly positive thing. So of course, it's a monotonic, right? Integrals over positive integrands have to be monotonic, right? So this is a useful quantity to know how to compute. And here's what you get from sine Gordon versus the truncation result. So the blue dashed line is a prediction from sine Gordon. And there's a black staircase line, which is you get from LCT, from the conformal truncation. And then if you do a little bit of processing, basically you get this red dashed line. And notice that it's just bang on with the sine Gordon C function. All right, so here I've shown you a comparison between the difference between what we get from the truncation and from sine Gordon. You can see it's better than about 1%. And then there's this one little dip here, which is because there's a tiny less than 1% difference between the mass of one of the particles. And so in truncation, it comes in a tiny bit earlier than it comes in sine Gordon. And so this dip is when it showed up in the C function in truncation, but it hasn't quite shown up yet in the true answer. All right, so you get this C function to extremely good accuracy. All right, so we're really seeing in the infrared of this model at small quark mass, we get the sine Gordon model. All right, so this was the details of how that smoothing was done, but I'll talk about it later. Afterwards, if people are interested. So good. So maybe 5 more minutes. Is that okay? All right. So so I don't know. Maybe I've made this sound too easy. It's still a hard business. So what makes this hard? What are kind of the messy bits that I didn't talk about so much? So first of all, one obvious thing is it's just hard to get enough states. All right. Exact diagonalization of a matrix has limits. Your laptop can handle about 100,000 by 100,000 matrix. That's about what it can do. You can do a little bit better if you have a sparse matrix and you use a cluster and you use various tricks, but there's always going to be some limit of how far you can go. And then furthermore, actually getting the matrix elements of that Hamiltonian is a lot of work. Okay, even in a free theory, it was a lot of work to compute all of these matrix elements. We think of a free theory as being solved usually, but actually just knowing all the OP coefficients of all the primary operators in free theory is actually quite hard. A much bigger issue is that divergences in a Hamiltonian framework are weird. Taking the cutoff in a Hamiltonian framework is a sort of terrible non-local thing to do. And you can get non-local state-dependent counterterms. So that's kind of easy to understand in physical terms. If I put a hard cutoff on energy, then that's a non-local thing that knows about, if you have some extra particles over an Alpha Centauri, that means your cutoff sort of here on Earth is slightly lower. All right, that's not usually what we do when we do cutoffs in QFT. Usually we do something where we do a cutoff on sort of the energies or the propagators of individual fields, not the total energy of the entire system. So understanding these state-dependent counterterms, I think there's been a lot of progress on this in the last few years, but it's still an important challenge. And then the last thing is preserving gauge invariance is hard, right? In 2D, we basically know how to do it. In 2D, we know how to preserve gauge invariance. You go to light cone gauge and sort of gauge invariance is fine. But doing it in higher dimensions is tricky. And one reason it's tricky is gauge theories don't really fit into this framework I described. They're not really theory, CFTs deformed by local operators. Even though we often talk about them as if they are, we think of them as being sort of a free theory deformed by A mu J mu. But A mu J mu is not a local gauge invariant operator. It's not really one of the operators in the CFT itself, right? So deforming by this is a bad thing. And in practical terms, what that means is once you do a Hamiltonian truncation, it's very hard to find a regulator that preserves gauge invariance, okay? So how might you do this? Okay, so finally, I'm coming back to the dream that Misha and Alexei were sort of kind of getting at earlier at the very beginning of the talk. This is the dream I wanted you to have in mind. So how would you try and do gauge theories in 3 and 4 dimensions? And what I want you to imagine doing is basically, it's really what Alexei said. Oh, don't we know if you have a gauge theory at weak coupling, hasn't that quote unquote been solved? Because you can just compute everything perturbatively. And that's what I want you to imagine, in your mind, sort of the future of this is. If you take Banks, Sachs, Caswell theory, so in fact, Caswell wrote the first paper on this, pointing out that at 3 colors with 16 flavors, the critical coupling alpha star is 0.04. So that's very small. So you could imagine just going out and doing a ton of work and computing all the anomalous dimensions and OP coefficients for that theory. That's a CFT. It's a well-defined CFT. And now if you want to study QCD, you add in gauge invariant relevant operators QQ bar for some of the quarks to gap them out. Okay, this is now a gauge invariant operator. So gauge invariance is not a problem. There are no gauge fields anywhere at all left over in this description. We're just starting with OP coefficients of gauge invariant operators, and we're deforming by a gauge invariant operator, right? So it's manifestly gauge invariant. You go in, you gap out, say 13 of the flavors, and you're left with QCD in the IR.
No, but this is a weakly coupled problem, which you describe this Banks-Sachs limit, right?
That's the point. Yes, that's the point.
It's weakly coupled
Yes.
problem, so you don't need to use all your heavy machinery because
Not for the CFT, but for once you deform by the mass terms. When you turn deform by the mass terms,
yes.
now the theory is no longer conformal. You turn on the beta function,
So you
and in the infrared, the coupling will become strong. So it's a strongly coupled problem once you turn on the deformation.
yeah, but then if you turn on many masses for many, not just for 1 or 2 flavors, but for many flavors,
Enough to exit the conformal window.
strongly coupled, but it's not conformal and it's not realistic in any way.
Sorry, the whole point of this talk was we're turning on relevant deformation, so the theory is not conformal. It is strongly coupled. That is the point. This is a method for doing theories which are not conformal, and they are strongly coupled. So that's why I'm proposing this.
No, but then you return below all the masses, you return back to regular Young-Mills theory. with a
Exactly.
different lambda, that's all. And all the
Yes.
scale of strong interaction just shift towards smaller energies, and you can forget about where you started.
Right, but you wouldn't be able to do a computation in terms of that coupling, right? This is a very different type of computation. This is, right, what you're saying is true of all the examples that I showed you, and I showed you that they work, right? The point was we started with the CFT. In the UV, we were able to those are free CFTs. We were able to compute everything in those theories because they were free CFTs, and then we turned on a relevant deformation that triggered an RG flow. And then below that RG flow, it really is a strong coupling. You can't compute anything perturbatively in that coupling. But the point is that's not what you're doing.
Okay, that's what I'm saying. Do you listen to me?
I'm listening to you and I'm telling you the reason that all the examples I showed you worked is because they're not doing perturbation theory in a small
Yeah,
coupling.
but these 2-dimensional theories are exactly solvable.
No. The whole point is that they're not. The point is 5-4 theory in 2D is not exactly solvable.
Okay, this trivial theory is not exactly solvable. Maybe it has some remnants of exact solvability. I don't know, but QCD2
Even if
is
okay.
exactly solvable, right?
no, you're not listening. All right, why don't we talk about that first?
He's going to smaller.
All right. So all right. So okay, what's the point of the future? Well, I already told you my dream. Okay, I didn't talk very much about doing 3D models, but there's been interesting work in 3D 5-4 theory. There have been a few papers on this recently where I think they have understood how to deal with the non-low curve counter terms. I think it would be very interesting to do something sort of similar to what Fiona referred to. You actually take all these eigenstates and you actually look at things like thermalization, transport, and hydrodynamics, which you can do because you have access to a very large number of energy eigenstates. And then finally, I think the 2D methods really are fairly well developed now. So we put this publicly available code. You really can just download the stuff. You can make most of the plots that I showed you in this talk. And there are a lot of interesting 2D theories which hasn't been applied to yet. And so I think there's quite a lot of interesting work to be done in that direction as well. So thanks very much. All right. Thank you. Yeah, Alexei.
So I have a question about this 2D QCD example you mentioned. So you had 3 colors and how many flavors? 2 or 1?
One flavor.
1 flavor. And this is just my ignorance. I don't remember. What is known about the infrared of this theory? Is it supposed to have is the anomaly really supposed to be matched by a boson, or is it matched by a fermion? How do you know?
The anomaly is, yeah, it's in the massless limit. The anomaly is matched by a boson.
Is that obvious?
Um,
I mean, if it was more like 4D QCD, yes, because we expect chiral symmetry break.
mhm.
In 2D, is it obvious?
I guess,
How do you know you don't have a massless barrier? I'm not saying I think there is one. I don't know. That's all. I mean, perhaps answer people in the past have studied it.
No,
The
for
expectation.
3n, for 3n, it's not exactly solvable.
It's not exactly solvable.
And
Yeah.
if you take, and the coupling constant doesn't run, because in 2D it doesn't run.
That's
So
right.
if you take from the very beginning with 3 flavors, large coupling constant, it may well happen that fermion is mass.
That's what I'm wondering. I mean, it's a logical.
Yeah, I mean, in general, I think it could have happened that way. That is a logical possibility. So usually there, the possibilities of what can happen in the IR is if you have an anomaly, it can be reproduced by, sort of the usual cases we talk about are there can be spontaneous symmetry breaking in the IR, and then you have a Goldstone boson, which can reproduce it. Or there's no spontaneous symmetry breaking, and then you can have a non-trivial set of massless degrees of freedom making some interacting CFT in the IR. And I guess a priori you could have had, yeah, I guess logically either of those are.
Could I interpret your results as an argument that it really is a massless boson?
Yes, you can just directly see that. So that's I didn't talk about this all that much, but in the limit, in the massless quark limit, it's actually an exact result at any value of the truncation that there's a massless pion. That's true for any. It's not. So this is kind of special. It doesn't go. Its mass doesn't go to 0 as the truncation grows. It's just at every value of the truncation there is a massless pion, and it's just manifestly a boson. And so
I have a few other questions. I'll ask them later.
Okay.
Yeah. Thank you.
Yeah.
So if I understood correctly, I mean, if overall your technique works if I have a CFT
Yeah.
solvable.
Yes.
You took either a 3 or a theory which is perturbed, like the dream example.
Yes. Yes.
But it won't work if the CFT is strongly coupled. Right? You get a strongly coupled fixed one.
Well, the problem is that if it's a strongly coupled CFT, then it's just unlikely that you're going to be able to solve it.
Yeah.
Right. But but so for example, in 2D, we know an infinite number of strongly coupled CFTs that we can exactly solve. All right. And so it's not important that the CFT itself is weakly coupled. It's important that it's solvable.
Yeah.
All right. So you could take, if you know how to solve the strongly coupled CFT, you just need to know all the 2 and 3 point functions in that CFT. That's it.
I was thinking more about 4D. No, I understand 2D more freedom, but in 4D, right?
Yeah.
Strong coupling, that's going to be possible to use the technique, right? You won't be able to solve it for CFT.
You're not going to be able to use, so in practical terms, your UV CFT is probably going to have to be weakly coupled because those are the ones we know how to solve. But that's still a huge number of theories that flow out of a weakly coupled UV
I'm
CFT.
thinking if there are some quantum field theories that are only close to strongly coupled CFT.
Yes.
And then you're never going to have a handle.
Yeah. Yeah. I mean, if I wanted to, yeah. Right. So I might paint another dream, which I think is probably unrealistic, that you might use something like the bootstrap to solve for the CFT data of a strongly coupled CFT. And then once you have that, then you go off. And so, the problem is you need a gigantic amount of CFT data. It's not good enough to have just like 1 or 2 operator dimensions. You really need a very large number of them. But, I think, something like that,
Saying that the conformal bootstrap would have to give you like 40,000 operators, right? That's what you meant.
Yeah, well, it depends on the example. So in the QCD example I gave you, the sine-Gordon sector was actually being described by only 77 operators in the end. So it depends on how efficient the convergence is. But maybe 77 operators is conceivable with the bootstrap. You don't really know until you do it.
If you try working in the Zyber's conformal window, not close to the right edge or to the left edge, where the theory is indeed strongly coupled, then find, for instance, in the middle of the conformal window, the anomalous dimensions or correlation functions or something.
But this isn't, that's not where this method works, right? So you're talking about trying to use this method to find the CFT. The way this method works is you have the CFT and you deform it.
Oh, but we have the CFT at the in the UV.
Yes.
It's asymptotically free field theory, no
Yeah.
problem.
Yeah.
In the infrared, it goes into the Zyber conformal window. So it's the both limits are connected by CFT.
Yeah, yeah.
Well,
Well, okay. Maybe, so that was what that's what this slide was, what I was trying to say with this slide. Yes, it's true in the UV, it's asymptotically free. So it's kind of like a free CFT in the UV. But this is actually a big deal. The fact that it's going from the free CFT to the interacting CFT is not just turning on a local gauge invariant operator, which, you know, if it were, that would be the way to go. I totally agree. You would start with the free theory with the gauge coupling turned off. You would deform by this, and then you would do this method. But the problem is, if you just try and do that, just what I said, and people have tried, you just get lots of contributions that break gauge invariance, and it's hard to handle them.
no more questions.
I mean, I think for the harmonic oscillator, like imagine that you were watching it right down and you're interested in the lowest five. Right, so then the terms that he's terming are terms where you wander like 4 to 50,000 energy quantum away. And so, you know, your perturbation. And so it's not permanent.
Thanks.
Over those terms that come.
Yeah, sometimes I think if you do something like truncation, where if you have a different choice between cases,
Yeah.
you have better results.
Yeah.
Like that.
No, I totally agree. So indeed, I think there's a lot of room for improvement by trying to choose a basis which, you know, if you can figure out something about the important features of the eigenfunctions of the true Hamiltonian, then you want to try and build that into your basis. Oh. Yeah.